Welcome everyone. My name is Mustafa Basri, a graduate student from Electrical and Computer Department, Khalifa University, United Arab Emirates. On behalf of my co-advisors, Arek Karaptian, Bilal Hassan, Majid Hanji, and George Diaz, I would like to present to you a hybrid deep learning approach for vehicles with sleep prediction in off-road environments. Our motivation in this paper is to develop a wheel sleep prediction model for off-road navigation. This is a crucial task for off-road navigation, especially on unpaved surfaces such as sand or crater area. The vehicle slippage is considerably high here, and it can affect the vehicle's planning, trajectory planning, and navigation in general. While on-road autonomous navigation has attracted quite a lot of attention, the research on off-road navigations and sleep predictions in the off-road environment has been in a nascent stage. So this motivates us to provide an accurate wheel sleep prediction model tailored for the off-road environment, especially for a car-like model. So in general, the factors that could influence tire slippage can be categorized into two: vehicle's details and also the properties of driving surfaces. Vehicle details could include the weight of the vehicles, the velocity, inflation of the wheels, etc. On the other hand, the type and properties of the driving surface can be sand density, rock frictions, terrain unevenness, in another word, the slope. The existing research work on off-road wheel slip predictions focuses mainly on a rover space mission explorer and tracked vehicles. On the other hand, wheel slip prediction for car-like model has been relatively unexplored. That's why, in the present work, we propose machine learning, deep learning, hybrid-based methods to estimate wheel slippage tailored for car-like models in the off-road environment. Toward this, we first identify the features that are highly correlated with the slippage car-like models, and also we propose lightweight and accurate terrains classification based on CNN models. We also provide a comparison of different regression methods towards the end. Moving on to our proposed methodology, here is the block diagram of the proposed framework for slip estimation. So we first gather the motions and geographical data, which is then fed to our proposed CNN-based model, which we coin as terrain net. And then after that, it goes to our proposed machine learning regressions, which we will output the final slippage estimation value. Later on, we will talk in detail about the terrain net and our proposed machine learning regressions models. But first, let's start with the geographical data collection process, as you can see in here. To accomplish this, we resort to an advanced simulation software called CM-Lag Vortex Studio. Why this is called an advanced simulator? Because it provides us with the very detailed kinematics and dynamics of the cars, as well as it based on the terrain mechanics or the study of the wheel-soil interactions from a well-known paper. So it can emulate and provide us with a highly realistic and accurate representation of the scene and physical worlds, as you can see in here. Based on this, we fed a total of 126,000 frames from 4 different terrains into a terrain net. The objective of the terrain net is to classify the types of the terrain, which is one of the important indications to select the machine learning regressions later on. Moving on, we are also using the same setup for the motion data collections. In here, we collected the torque, the velocity, accelerations, angular velocity, steering angle, and then the positions of the wheel in X, Y, Z axis. We also collected the longitudinal slip value of front wheels from the simulators, which are considered for the grounded purpose, Again, these values are all based on emulated physical theory mechanics models. The sleep calculation can be seen in equation 1, where r is the radius of the wheel, v is the actual velocity, and omega is the angular velocity. The sleep had values between 0 and 1, with 1 referring to the maximum sleep. The slope features data is calculated in equations 2. It is the arcsines of the front and back z-axis positions of the wheel compared to the distance from the front wheels and back wheels. Then we apply feature selection from this motions data so that we can get the most correlated features data to be fed into our machine learning regressions model later on. Now let's proceed to our proposed terrain net model. As you can see here, this is the architectures of our model. One important feature of this model that it is designed as minimalistic 52 layers to be suitable for real-time applications. Instead, conventional feed-forward processing, we use a model based on a directed acyclic graph network, and it incorporates the oscillospatial pyramid pooling modules and residual connections, which allow our model to classify the terrains with substantial high accuracy, as we can see later on in the result section. In our paper, we consider different types of machine learning algorithm, as well as we compare their performance later on the result sections. In particular, we deploy and designed multi-layer perception, which is a simple version of deep feed-forward neural network. It is a supervised learning approach that learns to map a functions. As you can see here, each neuron in hidden layers transforms the value from the previous layer with a weighted linear summations followed by a non-linear activations. Then in the training process, we fed the feature selection result, which has these terrain classification result characteristics, into our multi-layer perception model, which has these hyperparameters. Then we will get the wheel slip result at time t on specific terrain as we defined when we input the characteristic of these terrains. For ensemble learning models, we deploy random forest and extreme gradient boosting. As you can see here, random forest consists of multiple decision trees where each of the nodes related to our target class and attribute are characterized as internal nodes, whereas the XGB employs a boosting algorithm to improve prediction accuracy instead of averaging all the leaf nodes. For our models, both models parameters were selected and set based on 5-fold cross-validation. The simulation result of our terrain net can be seen in figures 2, where we compare it to the other lightweight pre-trained models. Using our test dataset, images uniformly dispersed over 4 terrain classes. And in figures 3, we can see that there is a class activation maps and a confidence score for randomly selected images of each terrain types that are correctly classified by the trained terrain net models. And in table 3, we have the comparison of proposed terrain net models with other paper methods in terms of computational complexity. As you can see here now, our terrain net has the lowest parameters and run times with the higher FPS. The simulation results for wheel slip estimations can be seen in table 4, where we compare the slip estimation performance of the regression methods. And as you can see here, XGB in the combined results achieves a slightly better performance over random forest in terms of MAE metrics, outperforming it by 6%. And you can see is as well almost in the other terrains, the XCB get the best performance. And for figures 4, we can see the predicted or versus actual ground wheel slip values on the test samples for each terrain types using the three regression method we have. As for table 5, we have the indirect comparisons of the proposed slip estimation result with the other paper methods. Since, to the best of our knowledge, there is no public data set that can be utilized as a benchmark for our evaluation for the slip estimations models. But here we have our proposed method that has the lowest error in all the matrices in here. As a conclusion, we propose a hybrid deep learning slip prediction models for off-road conditions. The proposed framework first identifies the terrain using an efficient lightweight CNN. We also identified the promising features derived from the sensor to be fed to the machine learning regressions. Unlike existing research that primarily focuses on sleep estimation for rovers or differential driverless robots, the main of this research is to establish a sleep estimations model tailored for a car-like robots. The model can be used to analyze the risk level of sleep and improve path planning based on the results. Thank you for listening.